off this week, which is nice.
Yeah.
That's why I got the donuts.
You had time and okay. Just have a couple. There's a couple little topics left. We're gonna finish this topic. You have one more homework for this. Okay, we're talking here about composite slabs and how you calculate it and where the key components are at. Okay, I should give you a minute to. I don't think we have a full 50 minutes of class stuff to cover today, so we'll just take some time.
That's what Tim said.
He said that.
Yeah, and
And then we were there.
And then
15 view and not finish.
It's hard to take notes while you're eating a donut.
But on the name thing for Tim's class, apparently on Wednesday, he clicked through 29 times to find my name specifically because I wasn't there.
Did you really do it?
yeah.
Nice.
And then it came up today, naturally.
Oh, it did. Did he added a component to it, right?
If it's his name.
If it's his name, it just clears. That's kind of fun.
I thought he said that was only if he was like that.
I don't think so. I think it's just if his name comes up with theirs.
Okay.
And then we talked timeline. Did your captains tell you that we're just going to try to have?
Sean hates this idea, by the way. Sean is upset.
What does Sean want to do?
I think we should just get it poured before end of the semester.
But then when are we going to break it?
Yeah, then we'd be breaking it during winter break.
That sounds like fun.
Like
Sean's gonna
during
be here.
Christmas.
Yeah, during
I
Christmas.
told Sean we should vote because it would be everyone to him.
Which is fair, but
I mean, so the idea was by the end of the semester, you have your designs all ready to go, and then we send it to them, and then we'll probably cast either the end of Christmas break or the first week of next semester, which is kind of weird because you're out of this class and stuff. But I'm gonna have to fail all of you beforehand. What's that?
I said the end of Christmas break would be cool because then we wouldn't have to.
Take classes off or something. Yeah, you wouldn't have to coordinate stuff like that. Yeah.
See?
So, right.
And then we'd be casting like when people are gone during finals, like,
Yeah.
That would
and then we'd be breaking either Christmas or New Year's. So.
Right.
Yeah, I'm not
Or we could. I mean, I guess. Do you have to break it at 28 days, or can you break it at?
No, but I guess if we just want the most
break it whenever
accurate,
we want.
we can break whenever we want.
Yeah. Does that sound good with everybody? And I'll just. And then obviously I'll grade you based off of like your designs that you submit early on, and then I'll go back and give everybody Fs that on the team that loses, and then everybody A's on the team that wins.
you could go back and change it.
Oh yeah, you're right. I'll give all incompletes then. I'll give everybody's getting incomplete, right? Anybody graduating?
Everyone's
Well, you thought you were graduating. You can't graduate with an incomplete, so I'm sorry. So,
I can.
yeah, you're graduating. You're not even going to be here anymore.
Yeah.
R.I.P.
R.I.P. But you can come back. You'll be in town, right? So you can come back and watch the break and stuff like that. So, but I think that's how we have to do. In the future, if we were to do this, like, because I like the idea of just being part of this class, in 2 years from now. I don't know if we could do it in this semester. It'd be really hard. Like, even if from the get-go we knew we were going to do it, but how are you supposed to design something when you don't have, like, we just finished, like, shear design last week. You know what I'm saying? Like, it would be hard to do. So it would have to be this 2-semester thing. So.
Or use the WashDOT.
Or just use a program to blindly
Yeah.
blindly decide.
Well, you could blindly design it and then prove it
Yeah,
after you've learned it.
right. I can see that. Okay, so we're talking about everybody finished eating their donuts because you got to eat another one because there's a whole.
Any more classes today, Mike?
I don't. I'm done. What about practice?
What?
Or your practice is done?
Oh yeah, we just lifted.
Oh, you just lifted today. You can't give it to them. You know where you could really pawn off donuts is Tate Lab. If there's people in there, it used to be the hangout spot. I don't think it is much anymore. Yeah, 'cause everybody's got their own laptops.
Friday after.
Yeah.
Throw in EMLC.
Oh, you can do EMLC.
Just throw them in there.
Yeah. EMLC. You could sell them. You could sell them in the EMLC. Sell them. Give them $1 a piece.
I'm in there.
Yeah, you can make some money on it.
Only for the students, not the employees, though.
Kyle, it's $2 for that. $2 for you.
I don't work today.
Okay. All right, everybody, we're good to go. All right, so let's go to this. Let's finish up our notes
Just kind of show up.
for this. Mm-hmm. Your hands are sticky. Okay, so we're on this topic right here. So this is the different load stages that we can control these designs and what you use. Like what do you use? Just the self weight? Do you use the dead loads and the live loads? What are we doing here? So this is the first load stage up here, okay? And this is just the initial load stage. This is exactly what we've done up to this point because the beam doesn't know it's going to have a slab on top of it at this point. So you're just making sure that the initial load stage is okay. That's going to be tension at the top and compression down at the bottom, okay? Everything is the same there. Then we come over and we do the slab placement. In the slab placement, again, it's the same equations. It's only the pre-stressed beam that's carrying anything. So we're still just using the pre-stressed beam properties, right? And what we're going to care about in this situation is going to be with the self-weight of the precast member and the self-weight of the cast in place because it has to carry the new fresh wet concrete that's on there at this point. It hasn't become composite. What we care about in this load stage is going to be compression to the top and tension down at the bottom of the pre-stressed member. There's nothing going on in the slab at this point. From here on out, those stresses are locked in place. Okay, the pre-stressed beam is carrying itself and the self-weight of the slab, and those are locked in place. From here on out, it's going to be a composite section, and we're going to then add on to it the composite stresses that are happening, right? So now the slab is acting compositely with the precast member, and so that's what this last one is that, okay? And so to calculate those stresses, this is one of the places we tried to simplify, or I tried to simplify from what Stanton's did above there. It just Stanton's above used this entire equation and put it right here. We could just know that it's going to be these stress. God damn it. Oh my God. These stresses right here, right? Those are locked in. So it's going to be those stresses. Oh, sorry, not there. This guy to here. It's going to be the stresses that are locked in from carrying the self-weight of itself and the cast in place, and then add on to it, just superimposed on top of it, the superimposed dead load and the live load. But now, instead of dividing by the S2 of just the precast member, we divide by S2 of the composite member, because that's going to change, right? Because this neutral axis moves. And so the S2 for the composite member is going to be slightly different. So you're just going to use that same value. You do this in a homework, by the way. That's where... Make sure we get this all F2S. Right, that's going to go, use this. Fucker. God damn it. I'm trying to use the new tools and I just... It does it. There we go. Clear as day. Right. That's the same variable right there, right? And it's a little bit cleaner way of thinking about it, right? Again, those stresses are locked in, and we just take those stresses, then we add on to it the composite. Yes?
You might have said this another day. Does the PCI give us...
Oh, by the way, I record the lecture. I just haven't uploaded it yet.
Okay, cool.
Okay.
Sweet.
Yeah.
I haven't looked yet.
Okay.
Please say, do you need that new section modulus for the composite, depending on a certain depth of...
Yeah, let's talk about that. That's a good point. Let me get through this, and I've got a little diagram. We'll describe these variables. Yep, perfect. Okay, so then this value here, F1 PC, is going to be down here. Yeah. Do you think it'll do this? Yeah. Oh, it did do it. Yeah. That's that value right there. So it's, again, just locked in. Okay, and then, so there's actually 3 places that we have to check, right? So this is just my pre-stressed member, right? This is going to be, this right here is compression top of precast member, right? Because that's just the precast member. Down here is going to be tension bottom. Is what that one is down there. And then the one in the middle here, we haven't talked about yet, but this is compression in top of slab.
Do the top of the precast member.
What's that?
Or,
Yep, I already got it. Why did I call it precast member? And this one I'm going to go call PC. So we already got the top of the precast member, but then we also have top of the slab we have to check, right? Because it has limits too. Okay, and you notice that this one, what's happening in the slab is just the superimposed dead load plus the superimposed live load divided by the S for the top of the slab, and then we have to modify it by that N, because remember that N has to do, we pretended it was something else so we could do MY over I, and now we got to bring it back to the actual stresses, right? And so we multiply it by that to take it back out to the actual stresses. Okay, or actually in this case, bring it back to the actual stresses because it'll be less than what you calculate there. Because N in our case, for this case, when we have the precast or the post or the casted place on top is the weaker stuff. We're doing the weaker is what we're transforming. So, okay, so let's talk about some of these variables to answer Will's question, just to clear that up. Right? If we've got rectangle like that, and then we've got underneath it our web. Yeah, that's, I don't like it. Oh, God damn it. Okay, fuck. I barely know how to use this thing as it is, and then when they change things. Okay, so there's my precast member down at the bottom. Okay. So your first thing you're going to have to do is calculate where the CGC is of this. Right? The CGC is going to move, right? It's going to move up. I mean, this is exaggerated because yours is going to be like a really big precast member and then like a small slab on top, so it won't be as exaggerated. But this, say you just had something like this. You have the precast down at the bottom, and then you got the casted place slab at the top. You have to find the new CGC, and that's just a weighted average, right? Just like you do the center of gravity of anything, do the weighted average. Start at a reference point, do the area of this multiplied by where its centroid's at, plus the area of this multiplied by where its centroid's at, and then divide by the total area, and then it'll tell you where the CGC is. So you're going to calculate the new CGC. It won't line up with the other CGC, okay? When we're talking some key dimensions here, this right here, right? That's what we're going to call C top slab. I mean, call it whatever. Just make it really. It's value because that we're going to the C to the top of the slab. Okay. Then we have another one that's going to make a difference, right? Or what we need to know, right? Is what this C is, right? Because this is taking me to the top of the precast member. So C top, or I guess we call it 2, right? I don't like to call it 2, but in my numbers over there, I call it C2. And we'll put a T on it because it's the C2 of the transformed section. Right? You could write transformed if you want. Because it's going to be a different C2, because you're going to have a C2 of just a precast member alone, and that's the distance from its CGC up to the top. But in this case, this is of the transform, so you're going to have a new one there. And then you're going to have one going down, too. This dimension is going to matter, too. Right? When we're calculating the tension at the bottom, we'll call that C1 transformed. Okay, and so in terms of the variables over on the side, right, this is going to be S2 composite member PC is just going to be I transformed, we'll call that IT, over C2T. Because you have to get, now this is the transform section property, so you're going to have to calculate I transform, and then it's over, I guess to keep it consistent, formed, like that, right? To keep it consistent with what we drew up above there. I guess you can call this transform too if you want. Okay. And then do the next variable, right? Which would be S1 composite PC in the precast member. It would be I transformed over C1 transformed. Okay. And then the last one is the S top slab for the composite member, which is going to be I transformed. I regret spelling out transformed. I really regret it. I should have just said T. T means transformed, but I tried to be as clear as possible, and I just regret it because I got tired of writing it. And this would be C top, what do I call it up there? C top slab. Okay. So those are the variables that you would use over there. Does that make sense to everybody? And the reason we care about that, right, is this top part's going to be in compression, so I care about what the compression limits are in my precast member, right? Because you can't go above 0.6 F prime C. So I need to compare that to the 0.6 F prime C, right? Also, up here at the top, my top of my slab is also going to be compression. I need to make sure that that is less than 60% of my F prime C as well, right? And it has a different F prime C, it has a lower F prime C, so you have to check that. I don't need to check the bottom of the slab, right? I don't need to check the bottom of the slab because that's going to have less compression than the top of the slab, right? So I just need to care about I go straight to there. So where your check and stress is the bottom, the top, and the top. Those three places are what we do it. So, and like I said, if you follow this, it's pretty straightforward, right? And you could do this in Excel, and you have to do this along the entire length as well, right? So this is the same kind of plots you used before. You do that with these if you wanted to figure out if it's okay along the entire length. Okay. Cool. So that's that. That's the composite sections. This is the elastic. This is all in the elastic analysis, just the initial pre-stressing stuff. You also still, in a composite section, you have to check the ultimate capacity as well, right? You have to check the full moment capacity. And to do that, this is the easiest way to talk about this. And then it talks about it briefly in the code and just says, just use mechanics and figure it out, okay? And so what happens with this, it's interesting, right? Like in the reinforced concrete code, it tells you the rules, right? It says, use Whitney stress blocking compression, assume elastic, perfectly plastic steel, do this, but it never gives you an equation. It just lays out the basics behind the mechanics, and then you have to calculate it. And they do that same thing here. They just say, keep with those same mechanics. And all that changes really is when you go to the Whitney stress block, you just end up with two compression areas. You have a compression area up here for the, you son of a bitch. Is that funny, Neil? Is that funny? Is that funny, yo? It is kind of funny, isn't it? Like, why the hell? Yeah. Nailed it. First try. And then there'd be another part that if it's going down into the web, right, and it has a different strength concrete, right? It started out a block. Yeah. Nailed it. First try. Okay.
I think the sound effects are what.
Hey, that's right. You gotta make that if you want it to work. Okay. You'd still have this FPS down below, but then you would have, this is, 0.85 F prime C of 2, right? For the whatever the second one's made out of, and this one up here would be 0.85 F prime C 1. Right? So if that makes sense, right? You just if the top, and this is still A. This is still A. Oh, you son of a bitch. Right. That's still my distance A, right? We still don't know what that neutral axis is, and so you start out with that, And just because it's two different strengths of concrete, they just that's why there's two blocks, is because there's two different strengths of concrete, right? And so then over here, when you look at forces, my forces will be, you'd have one that's coming in at the centroid of this one, that's up in the flange. You then also have another C coming in here. You'd have a C1 and a C2, and then you'd have a T down here. T is equal to FPS times APS. Right? And you do the same thing. You just start out with this, and then you say sum of my forces are equal to 0, and then that'll tell me what my neutral axis location is, and then I sum my moments about one of the points, and I get my total moment carrying capacity. So that's what's also pretty sweet, right? It's weird that the code just lays out the mechanics, and then you have to figure out what the equations are they're using. One thing that's sweet about it is that you just apply those mechanics to all different shapes, right? We didn't change anything, so we just used the same mechanics that they laid out. We did this. If you had a triangle, right, it's the same mechanics that you use, and so you kind of derive the equation as you go along. You have to be smarter to do this than you do for steel. To be part of the hood. To be part of the hood. You guys are in steel right now, right? It is kind of nice though, isn't it? Or just like predictable. No? It's too hard though?
See the last homework was.
Yeah, it's fine until you start designing shit out of the appendix.
Yeah. Especially where the homework is on something where they spent 30 minutes talking about the homework, and then instead you were proctoring an exam for me.
No.
That's really funny that he said that he was going to record it, and then he just didn't record it.
I feel like we never had an intention of recording.
It was just tricking you.
yeah.
He was tricking you guys. Yeah, I'll record it.
Like for help, and he was like, I was talking to him, he's like,
Right.
he
Well, the
wasn't
notes
giving
you
me
gave us
anything
was
until I was
the
like, I wasn't there. And he's like, oh, that's right.
All right, all we're going to say about the shear design is the same procedure as non-composite. Which was fun, right? You had fun doing that, right? The V, I, and MCR equations change slightly. And then the last comment here, added complexity if centroid ends up in slab. There was one of the variables you used that had some language in there that talked about if your centroid was in the flange or in the slab up above, then you have to end up using like the border between the two as opposed to the centroid. So it just gets a little bit complicated. But other than that, it's the same. Right? Horizontal shear. We talked about horizontal shear before. And that's just, right? If you got members that are going, you got this guy going like this. Underneath it like that, right? You have to tie them together, right? And there's a section of code that discusses that, right? It's ACI 16.4 talks about horizontal shear transfer and basically what that rebar on top, like what spacing it needs to be and how much it sticks out and if it needs to be hooked and stuff like that. That's all covered in 16.4 or in AASHTO it's 5.8.4. We're not going to do it, but just keep in mind if you end up doing that, you have to include that. Okay, deflections. I think we're going to use transformed section properties for deflections after slab cures, I guess. After slab placement, I guess. Right, before though, deflections from before slab placement are locked into beam. So you basically just do deflections of just the pre-stressed beam itself, right? And then it's gonna, it under its own weight, it's gonna deflect down a little bit. You cast the slab on top of it, it's gonna deflect a little bit more, right? And then that's like the starting point. The starting point, so that'll be a known deflection, and then you put the slab on top, and it cures, and then they act together, and then now all the superimposed dead load and live load that come afterwards then use the transform section properties. So you'll have to pre-calculate the sag that comes from just the pre-stressed member and the self-weight, and then you then add on to it the transform section property deflections, okay? And then the total deflection is them added together, right? We're almost there. All right. Okay, so that's it for the composite members. You have a homework. I don't think you calculate deflection. I think you're just checking to make sure that it works. And I said before you have plots, and I can't remember if I have you do the plots or not for the precast. It might just be calculating at one point on the worst case scenario. Okay, so some loose ends, some things that we made assumptions from about at the beginning. We're just going to kind of show you that it was okay to make those assumptions, okay? And there's this one. It kind of afterwards, when I've taught this class in the past, I was like, I needed a little bit more to talk about. And I was like, this would be a good thing to talk about is these loose ends. So one of the things that maybe has set right with you, or maybe you were just totally okay with it, was that when you have a beam that's pre-stressed and you apply a load to it, it's going to stretch the bottom out a little bit more, which means the steel stress is going to go up. Right? But we ignore that. We ignore the fact that the steel stress goes up. And is that an okay assumption? I'm going to show you that just with a simple calc here that it is probably okay. Okay, so it's probably okay to make that assumption. It will be. So this is just a beam, right? It's a pre-stressed beam. It's 30 inches, 12 inches, 30 by 12, and then it has distance down, an EP down to the pre-stressing of 10 inches, right? So it just goes down there, and that's where my pre-stressing steel is at, okay? It has these properties. My area pre-stressing steel is 1.2 inches squared. It has a span of 30 feet. F prime C is 6,000 PSI. Here's my EC is 57,000 squared F prime C. Here's my I for this section over here. My FPE, so we've stressed it to 189,000, and then EPS is 28,500. Okay, so what we're gonna do is we're just gonna look at the self-weight. Right? If I take the self-weight of this member, right, it's not super light, 30 inches deep by 12 inches wide, so this is a hefty beam, right? We'll just look under self-weight and see what the self-weight alone does to the pre-stressing, okay? It's kind of a journey to get there, but let's do this. So first I'm going to figure out what the moment from the self-weight is. M self-weight, right? That's just going to be WL squared all over 8. All over 8, right? And so in this case, it's going to be 375 pounds per linear foot. That comes from the density of concrete. There's my 30 feet squared divided by 8. It's the moment at the center of simply supported. This ends up being 42.19 kip feet, which is equal to 506.25 kip inches. Okay. All right. So we got that. Now what I'm going to do is, given that moment, I can calculate the stress in the concrete. Do just to this. Stress in the concrete. I really want the stress in the steel, but I got to go through concrete first. So the stress in the concrete is just going to be M. So we'll call it F conc. F concrete. We'll say at pre-stressing. F concrete at the pre-stressing. That's just going to be, right, my over I. Because this is under elastic conditions. We're not going ultimate. So under elastic conditions, we can just do my over I. And so this is going to be M self-weight, which we just calculated. The Y in this case is going to be EP, because I'm trying to find the stresses at where the pre-stressing is at, and where the pre-stressing is at EP, right? This is the CGC, and you go down, EP is what the Y is in that equation. So M self-weight, pre-stressing, and then that divided by I. Okay, so what we get here is 0.188 KSI. Okay, so the self-weight, applying the self-weight changes the concrete stress by 0.188 KSI. Okay, so barely changes the concrete stress. Okay, but what does it do to the steel stress? This is the journey. Okay, so what we're going to look at is what strain, so here, let me take a step back. Right, it's all based off of this. Here we got I don't like where that's at. Right, it's got stresses that look like this, right? Right, and I'm calculating what the stresses are right here. This is my F. My FC. So when you do MY over I with this stuff, you're actually figuring out what's happening in the concrete. So what I just calculated right here was this change and this change right here. Okay, is how much did the concrete change? But the concrete stress change is not the same as what the steel changes. They're locked in together, right? But they don't move the same. Or sorry, they're locked in and they move the same, but they have different stresses. The steel's going to have a different stress. It's a lot stiffer, so the change in strain will give us a bigger change in stress. So at this point, I need to calculate how much did the concrete move? Okay, if I know that the stress of the concrete is 0.188 KSI, how much did it move? And I do that just by dividing that number by the elastic modulus. So if I do that number divided by elastic modulus, it'll tell me the strain in the concrete. Okay, so then I do that. Strain concrete at post-tensioning or pre-stressing is just going to be the F concrete at PS divided by EC, E of the concrete. Okay? And if you carry that out, in this case, you'll get 4.258 times 10 to the negative fifth. It does not move very much in terms of strain. Okay, but now I could say, well, the steel, since the steel's right there at the same location, the steel moves the same. So the steel moves the same. So now if I try to figure out how much did the stress change, I take E of the pre-stressing and I multiply it by that strain. Okay, and so if I want, this will be change, I don't like that, delta FPS. My change in pre-stressing would be the strain in the concrete at PS times EPS times the elastic modulus of the pre-stressing. And if we do that, we get 1.214 KSI. Okay. So is that a big change, 1.214 KSI? No. What did we start out with? 189,000. Okay, so we started out at 189,000 KSI, right? So versus 189,000 KSI. Right? Does it change? Yeah, right? This again is just a self weight over 30 feet. It does change. It changes 1.214 KSI out of 190,000 or 189 PSI. PSI. Hold on, I wasn't done. I was like, boy, that's a huge fucking difference. I kept thinking that, and I was like, PSI. Well, how about this? Oh, God. This is better. Instead of comparing PSI to KSI, it will make both KSI. Yeah. So even then, right? 189 versus less than 1% change, right? Did I do it right? It was a weird comparison, I know. Okay, now, that's not a big difference. That's just a self-weight. But you can imagine, you put the live load and other things on there, that number will go up. But the order of magnitude is going to be in the same vicinity, just for an example. So now I know all of you you're uneasy about it. You didn't like it. There you go. It doesn't make that big of a difference, okay? A little fun journey. Take on a journey here. Okay, so then you go over here. Now, another assumption that we made was that we ignore the effect that pre-stressing has on the elastic modulus. Right? This one you may not. You do this in regular concrete too. When you calculate the section properties, you ignore the steel as being part of it. Right? When you're calculating deflections and stuff like that. Is that okay to do that? I mean, to do it the right way, what you should do, I already filled these things out. Lucky you guys, huh? Lucky you guys. Right? But if you're being a stickler, right, you should do transform sections on this. This would be, or this one we're transforming the stiffer material. So we've gone the other way this time, right? Yeah, look at that. And so we've gone the other way. So and you could do either way, right? So then, is that okay? So based off of this, right, is this okay? So really what you would do, right, is you would need to do transform section properties in order to do this right, okay? So then you do the ratio between the pre-stressing and the concrete, right? You have to calculate that. Oh, I didn't fill out all the parts. This right here would be equal to, in this case, 28,500 divided by 57,000 times square root f prime c. And if you take care of all your units, this ends up being 6.45. It's a big difference. That's a big N, right? Because now we're going, instead of going between, a weaker concrete and a stronger concrete, we're going steel and concrete. So there's a big difference. So a value of 6.45. My I, just in general, what we would use in actual design would be 27,000, right? That's I of just the rectangle, okay? And in this case, my AP, this is the same section from above, by the way, that is 1.2 inches to the fourth, okay? So then you got to transform, this is where it gets a little weird. You have to transform this steel, right? And before, right, we had a known width, like we had the two different members like that. We had a known width, and so we just changed the width of it. Here, we always just assume that steel is concentrated at one point, so it doesn't really make sense to change the width. So what you change is the effective area. So instead of transforming the width, you could just transform the area of the steel. So the area of the steel was originally 1.2. We multiply it by the 6.45. And so we treat it as if it has an area of 7.75 inches squared. Does that make sense? It's like, this is not like we don't have a known depth of the steel. We just say there's steel at that location. And so you have to transform the area as opposed to transforming the width, okay? So then you have to calculate. So now we know that that's changed. We have to calculate where what my YT is, okay? And it turns out to be 14.78, but I'll show you where those calcs came from, right? Because you end up doing this a little bit in your homework because you have to find the transform section properties. I'll kind of show you how you would do that. So now I find where is the new centroid. It's going to be down a little bit. It's not going to be at 15. It's going to be down a little bit because now I've got this extra little weight that's down below here, okay? So this is going to be, what you do is a weighted average, right? So it's going to be 12 times 30. So this is the rectangle, and it says the centroid is going to be at 15. Right? So it says it's going to be right in the middle. Then I add on to it the area of the steel, which is 7.75, and I multiply that. It says it's going to be at 5, right? So I picked the bottom as my reference point, and so middle of the centroid of the concrete is just going to be half of 30, so that's going up there, and then I'm going right there. So it's going to be 7.75 times 5 in that case. And then I take that, and I divide that by the total area, which is 12 times 30 plus 7.75. Right, and that's where that 14.78 came in. So that's where it says that centroid is going to be, is at 14.78. So it'll be coming from the bottom here. It just shifted it just slightly. And that should show you this. It's not going to affect it too much. It just bumps it down just a little teeny bit, okay? I don't know what I did here. I don't know what this is. I'm gonna, do you have this filled out on yours?
Yeah.
Yeah, it's wrong. Is it wrong? It is slightly wrong. I mean, it's close enough, but I'm just, okay, we're okay. Is that okay? No, that's not right. That's not right. That's not right. I never make mistakes, but that's not right. So now my I transformed is going to be, right, it's going to be I1 plus A1 D1 squared plus I2 plus A2 D2 squared. Okay, this is parallel axis theorem that you do there. Okay. This is of the first one, right? About the new centroid. That's the second one about the centroid. This is the steel about the centroid. Okay, so just fill in those values there. IT is going to be equal to 27,000 plus 12 times 30. That's the area of the first one times the distance there is going to be 15 minus 14.78 squared. My answer above on the right left out. It left this out, but technically that needs to be in there. But I think the reason I left it out is this is a really small number. 15 minus 14.78, so that's really small. And then you square it, and so it ends up being small. But it does change the answer slightly. And then you add on to it now. This would be. It has no moment of inertia about its own axes. And so I2 is this component right here. This right here is 0. It doesn't really, it's just all concentrated again at there. So then we're just going to add on to it the 7.75. That's its area times 14.78 minus 5 squared. And then what we get here is, what we get there is 27,759 inches to the fourth. Right? And that's versus what we would have used, which is 27,000 inches to the fourth. And I got 2%, 2.8% difference. Okay. So again, I'm okay with that. This is, there's a lot of that stuff built into a lot of our equations and stuff, these assumptions as we go along. I would say I'm okay with that too. Don't need to use transform section properties. This is concrete, for God's sakes, right? We're just guessing on the, it's all just a guess, right? So like, is it okay? Absolutely. Just especially you see that this doesn't make that big of a difference. Right? I had an advisor who used to say, it's concrete, you mix it with a shovel. Like, what do you expect, right? Like it's not an exact science, but it kind of gets us in the realm. Here, one thing I've always had problems with is structures too, when you have predictions of how strong those beams are supposed to be, and that they're not. They're like different, right? You're like,
Yeah.
Wouldn't it be cool if you were like, oh, let me just predict exactly, and then you break and it's like, oh, it broke exactly that, and this doesn't, right? And
I
it's
feel like the steel plates is usually pretty accurate.
yes, but then steel, like that one. I mean, that one. We used to have to do to get your master's here. You used to have to do a professional paper, and that was one of the structures 2 TA's professional paper came up with that lab. He made it, which is pretty cool. This is the steel plate one that has the 3 holes in it, and you pull it, and then that one's really cool because like what's off is what the ultimate like. If you have an assumed FY and assumed FU, that's what's off. Once you test one of them and you figure out what FY and FU are, you nail it. I mean, this is like right, it breaks exactly when it's supposed to. And then you have the holes, right? And then if you put the holes next to each other, it rips through 3, but if you just move it just a little bit, then it rips through the 2. But after the whole thing yields. Like you predicted that it's gonna do that and it does the whole thing. It's so sick. And then there's concrete where it's just like, I think it's just a huge guessing game, right? Okay, the other thing, I've said this one several times, right, is we do assume that the steel is only going one direction. Right? We assume that that the steel is just being pulled that direction, and we don't take into consideration that it actually is going. Oh, you son of a bitch! That it's actually going like this, right? It has 2 different components to it, right? And then is that okay? Did anybody ever, you use this? We use this part in the shear design, if you remember. Right? That's I don't remember what the variable was, but VP.
Yeah.
VP, right? That was the vertical component. I think it's a really, did anybody look to see what its magnitude actually was? It's really small because, right, we never draw these things to scale, but like from here to here, if it's a 30-foot span, that's 30 feet, and then it rises 3 inches over 30 feet or something like that, right? So it's a very small component. And so I say that it's, just keep in mind that we are inconsistent, and we're okay with that inconsistency. The last thing that we ignore is second order effects, right? You know what second order effects are? Right? I mean, it's just this is a second order effect. Like if you bend this thing, right? That this actually causes a moment, right? Like we ignore it, right? So because if this thing, I guess you have to put in a lateral load too. Like this thing gets analyzed in its undeformed shape, but really it deflects a little bit, and that little bit of deflection would then cause a moment down at the bottom. That happens with our pre-stressing as well. Once you analyze it in this shape, but then as soon as it bends a little bit, now there's some second order effects, right? Because now it's out of place, and then it's doing this, and so there's an additional moment caused due to that deflection. And the only way to capture that would be to analyze it twice. That's why it's called second order effects. Is you analyze it once in undeformed shape, and then once it's been deformed, you analyze it again, and then that moment would show up, and then then it's going to deflect a little bit more, and so then you can analyze it again and again and again, and it'll converge on the solution. We ignore that. Right? That's something we just, again, we're not going to do those calculations to prove to you that we ignore it, but we do in fact ignore it. And it will, I mean, it really does affect things, but just not that much, not worth doing. That's it. This little video, I don't know if you have that in your nose. That's just that video of the thing being taken up I like to put these little things in my notes, and then I was like, what is that? And then I go search for it, and then in this case, it was that big beam working its way up the deal. So that's it on the pre-stressing. Okay, clap. So on Monday, we'll meet Kyle. He'll do 50 minutes. And then he laid it out. It's going to be 6 lectures. He's going to do the next 2 weeks. And there is going to be a little homework in there or an exercise or something that he has like an example of actually applying it. I think Elias, again, nobody knows who Elias is because he graduated 2 years ago. But Elias just went into practice, and he said that this is the most valuable thing that he learned in this class was not what I taught him, but what Kyle taught him. But you can't understand Kyle's stuff unless we've gone through the stuff we did do, right? And then that'll leave us then we'll aim for doing the exam sometimes at the end of Kyle's stuff. When we get a little bit closer, we could talk about it. So 2 to 3 weeks out, maybe 3 weeks out. Should we set a time? Not yet? Not ready? Not ready for that commitment? Yeah. You like scheduling?
We'll work out. Let's do like next week.
Oh, yeah.